Hey, welcome back. Today we're going to be talking through how to deal with net force problems with three or more charges in a line. So specifically we're talking about using Coulomb's law and applying it, usually in the context of some physics class that students need to learn how to understand how to do this. And I'm assuming you've done a little bit of Coulomb's law intro already. If not, I've got a link to a video in case you're curious in the upper right about now. But what I'm also going to do is show you exactly how to apply Coulomb's law in a way that will be efficient and makes sense. The first thing we need to do is run Coulomb's law 3 times so we can solve for the magnitude of the forces in between the three charges that we have to deal with. So the force between 1 and 2, Q1 and Q2, the force between Q2 and Q3, and the force between Q1 and Q3. So let's go ahead and do that. I'm writing microcoulombs here to save space, but remember that's going to be equal to times 10 to the negative 6. So I'll write that up here. And remember, this problem gives us the distance in centimeters. We're going to have to convert that into meters, so just be careful with something like that. Alright, and notice that we do get a couple negative signs. I'm going to add in this negative sign here initially. Between 2 and 3 and between 1 and 3 we get negative signs, and that just means that the directions of the forces are going to be attractive rather than repulsive when we first start this problem. I know that the right side, the last numbers are cut off a little bit, but I think you can get the idea of what we're talking about here. Let me label the forces that we're dealing with. So if we look at the interaction between 1 and 2, remember, this is going to be repulsive. One way we know that is we get a positive response out of Coulomb's law. Another way we know that is just conceptually like charges repel. So this we'll label as the force on 1 from 2. This is also the force over here on 2 from 1. Remember, forces come in pairs, and these are going to repel each other. Next up, we have the force between 2 and 3. Because they are opposite of each other and we get a negative response out of running Coulomb's law, we're going to end up with this being attractive over here. So you could call this the force on 2 from 3. And similarly, this is going to be the force on 3 from 2. Notice that the magnitude that we had solved for in running Coulomb's law is actually going to be exactly the same. It's just the directions are going to be different. And I want to remind you that a lot of times as physics students, we don't oftentimes see forces in pairs, because we're usually just drawing a free body diagram with the forces on one object. But anytime you have a force, you have an equal and opposite force acting as well. Alright, and the last force we need to keep track of is going to be the force on 1 from 3. That's going to be attractive. I'm going to draw this offset over here. This is the force on 3 from 1. Now, I'm not trying to draw these as being proportional right now just because I'm trying to save space, but you get the idea. So for instance, the blue force that we have is 32 newtons. The red force that we have, like 5.5 times greater than the red force. So that would mean the blue line should be about 5.5 times longer than the red line. If we're going to draw this in a proportional way, that's okay as long as you get the idea. Here you can apply that later if you so choose. Oh, one more thing. Let me drag this over so we can more easily see what had been cut off on the right-hand side. Alright, let's consider this to be positive in terms of direction, and this direction over here to be negative. So to the right, positive, to the left, negative. And that's how we're going to think about how to summarize these forces here. And so let's say we want to be able to come up with the net force on each of these charges. So the net force on 1 are equal to the force on 1 from 2. And in this case, we're going to make that a negative value. That magnitude, we're going to make it a negative value. Plus, because we're just saying the sum of the forces on that object, plus the force on 1 from 3. And in this case, we are going to make that positive. So let's go ahead and just find what that value is. If we plug in those numbers, we have a minus 21.5 newtons. Now notice I'm going to make that a positive here because in the second half of the problem, so the first half of the problem is on the right side of the screen, second half of the problem, now positive, negative, are going to have a different meaning. They're meaning the direction, and that's really crucial. So notice that this was originally a negative 5.5. In fact, I started to write that, but then I remembered, oh, that was just telling us it was attractive. Those forces were attractive to begin with. So if we do the math here, we can say the sum of the forces on 1 are equal to about 16 newtons in the negative direction. So we're going to call that negative 16. Then if we're going to solve for the sum of the forces on 2, notice here I'm going to make both of these values positive here because the forces on 2 are both heading to the right. And lastly, we're going to do the sum of the forces on 3. And notice I've made both of those forces negative, again signifying they are being pulled to the left because the third charge is a negative charge. Alright, so hopefully that clears things up about how to approach a problem like this. I tried to put it all on one screen as much as possible so you can see all of the calculations all at once, how you would approach this. If you have any comments down below, please let me know, and I hope you all have a great day. Take care.